tutelus is tutelus 6 and left 5. But for group 3, so group 3 will be doing binary tree and Q. Because next week, group 3, no labs. Okay? Group 3, no labs. Yeah, not group 3, my group 1. Sorry, group 1. Okay, so my group this week you will continue binary 6, 3 and Q, because next week you don't have lab. Okay, I give you holiday for the liar week. Okay, so we continue. Okay, binary tree. So what is binary tree? So as you learned last few weeks, the structure is basically the linear structures. Okay, one by one means there is a link from one node to another node. So tree is a bit different compared to linked list, stack, and queue. Okay? Why? Because tree is a non-linear. Okay, what is mean non-linear? Means the arrangements of tree is follow or organized in a hierarchical structures. So basically, you need a root, okay, a root element. So from the root, okay, example, let's say we have this tree. So the root is the computer hardware. So from the root elements, basically we have many children. Okay? And then this arrangement is in hierarchical structures. Okay, and then from memory, you can have or many children as well. Means you can have a subtree out of this computer hardware. So tree, the structure is non-linear, and then all the elements are organized in hierarchical. So always remember the rules is a tree must contain, this one wrong, elements. Yeah, only one root element. So from the root elements, you can have many child, and then each child you can have many children, and so on. This is the structures of tree. Okay, next. And then tree also is or restructures. Okay, why we call restructures? Because from one tree you can have subtree. Okay, example, let's say this tree 17. So 17 is the root element. 9 is the child elements of 17. From 9 you have two children, 6 and 5. So 9, 6, 5 is basically another subtree. So this subtree later you can have another subtree. This means it's a recursive. The thing is recursive. So that's why later in the coding, okay, implementation part, we need to use a recursive functions to implement the tree. So later you can see a lot of recursive functions for the tree. Okay. Okay, now we look at the types of tree. Okay, the types of tree. So the first type of tree is what we call a binary tree. Binary tree. So in binary tree, the tree can only have two children. Compared to the first example, this is different. You can see memories, there's 3 children. So the type we study is what we call binary tree. This binary tree, the rules is the parents can only consist of 2 children. Example, 9, you have 6 and 5, that's all. Okay, you cannot have 3 children. Then 17, you have 9 and 15. So means each parent can only consist of 2 children. So the node to the left, we call left child. Left child. Example, 6 is the of 9, and then 5 is the right child of 9. Okay, so same thing applies to this. 9 is the left child of 17, and 15 is the right child of 17. Yeah, so this is the definitions. And then that has no children is called a reef. So these are all the reef without children, like 6, 5, 8, and 10. All this is the reef, no children. Okay, remember the terms. Okay, so we continue. And then the next term is height. Height. Okay, so what is the height? Height is the maximum numbers of nodes from to the leaf. So starting from root. So we count the maximum. Okay, the maximum. Okay, example, let's say we follow this path. So 1, 2, 3, 3 only. So it's not the maximum, means from the root to the leaf. This is not the maximum. Okay, this is 3 only. Okay, let's say we follow this path. 1, 2, 3, 4, 5. Still not the maximum. Okay, this is 5 only. 1, 2, 3, 4, 5 until the leaf. So you must get the path, the maximum path from the root elements to leaf. Okay, so in this topology, so we can see that this is the path lah. 1, 2, 3, 4, 5, 6. So this one is the maximum. Maximum from the root, the leaf, maximum. Yeah, this is height. Okay, so we have learned a few terms. Okay, new terms. Example like left child, right child, leaf, and then the height. Okay, because later when we implement the binary tree, we must know how to implement all this method. Yeah, clear? Next. Okay, so there are many ways to traverse a tree. So like previously when we study linked list, okay, if you want to traverse the linked list, you can any positions, yeah, from left to right. If double linked list, you can left to right, right to left. Okay? So if circular linked list, when you go to the end of the node, it will point back to the header. So binary tree, they also have different ways to go through the or search the tree. Okay? So we have pre-orders, in-orders, and post-order. So later we need to go through this algo. Okay? So for each of the traverser, there are different ways to get the elements. Okay? So as you can see, if it's a pre-orders traverse, so means we need to go to the root first. Okay, visit the root. After that, go to the left tree. After that, go to the right tree. This is pre-order. In orders is a bit different. The sequence, we need to visit the left first. So from the left, then only you go to the root, then only you go to the right. And then post order is different. Post order, we go to the left first. After that, go to the right. Finally, go to visit the root. So from the definition, I don't think you understand what is the how they search the tree. So later we'll go to some example. Okay, let me copy this algo first. Yeah, so later we'll go to the example one by one. So this is the formula. Okay, next. Okay, let us look at this one. So we start with pre-order first. Okay, you don't look at others. Look at pre-order. Okay, so the pre-order algo is you need to go to root elements. After that, go to left. Finally, go to right. Yeah, so D will be your root element. So they will display D first. You look at pre-order, they will display D first. After that, go to the left. Okay, go to the left. Left 3, B is the root element, so display B. After that, go to the left 3. Left 3 again. So A is the root element, so display A. So after you finish display A, no more child. Okay, so no more child, you come back to B, check any right tree or not. Yes, C. So you display C. So after you display C, check any children. Okay, no more children. Then you go back to D. Okay, so from D, you need to check the right tree. So right tree, you have F. So F means is the root, so you display F. Check any left tree? No. Any right tree? Yes. Then you go to G. So G, because you need to visit the root, so you display G. At the end, check any children in G? No. So the answer is D, B, A, C, F, G. This is how they traverse to the tree using pre-orders. So you need to understand this type of searching, right? Means visit the root, go to the left subtree, go to the left subtree, so no more, go to the right subtree, no more, go to the right subtree, no more, go to the right subtree, no more. Done. This is pre-order. Yeah, clear? Okay, before we go to in order, post order, another example. Go to the next one. Yeah, so we look at pre-order, same thing. Okay, so first we see the root P. So display P first. P. After that, go to the left, display F. Go to the left, B, display. No more. No more, we see the right, display H. Go to the left, yes, G. Okay, no more. No more, go back to this. Go to the right, S. So display S. Go to the left, R. No more. Okay, go to the right, Y. Go to the left, T. No more. W, right, Z, right. So the answer is PFB HGSR YTWZ. Okay, any questions before we proceed? Yeah, so this is the algorithm. If you want to visit the tree using pre-orders, so we follow these rules. Visit the root, visit the left subtree. After that, we visit the right subtree. Yeah, clear? If you have any question, you just type in the chat box. Okay, nothing. It's okay. Okay, now we go to the second one. Go back to the previous slide. Okay, the second one is in order. In order. Now we look at the in order algorithm. Yeah, in order. Okay, so in order, the searching is different. Okay, the searching is different. So for in orders, we need to visit the left first, then only you visit the root. Finally, you visit the right subtree. Yeah, so we go to D first. So D is the root element. So according to the algorithm, you need to go to left. Okay, go to left. Go to left. Okay, no more, no more. See, no more. So you display A first. You see, A first. Yeah. Okay, after that, visit the root. So B is the root. So root. So display B. After you visit the root, then visit the right subtree. See? Okay, no more. No more. Go back to the root. Okay, root is D. D. After finish, visit the root, visit the right subtree, F. Okay, no, there's nothing here. Okay, because there's no left tree here. So we display the F. Okay, after that, visit the right subtree. Because nothing here and nothing here. So we display G. So in order is A, B, C, D, F, G. Okay, another example. Okay, same thing. Okay, so for in order, we need to go to the left. Okay, go to the left. So B, go to the left, go to the left. Okay, B first. B. So after display the left, display the root. Okay, display the root. Then visit the right subtree. Because this right subtree consists of another left subtree. So we need to go to the left first. So B, F, G, H. Done. Done. We go back to the root. P. After that, go to the right subtree because the right subtree consists of left. So we go to the left first. No more, then only go back to S. Okay, go to Y because Y consists of left subtree. Left subtree, T. Okay, so because no more left subtree here, so the algo will display T. After that, display W. Okay, after W, then we go back to Y and finally display Z. Okay, one student asked, is it like the step solving the maze? No, no. Solving maze is totally different. Solving maze is you backtrack. Backtrack. This is not backtrack. This is to search the tree. Okay? But when you search the tree, they follow different orders. Pre-orders, in orders, and post order. Just like what we did. Infix, prefix, and postfix. For the expression one, yes, that one is correct. To solve the maze is different. That one is backtracking. Okay, lah. So if you encounter the in orders, okay, let me go back to the in orders. You can see basically when you visit the in orders elements, they are sorted. See? A, B, C, D, F, G. Sorted. See? Sorted. Okay, we go to the next one. In order. See? B, F, G, H, P. Sorted. Okay. So it means the in orders algo basically will help you sort the three nodes. Yeah, but pre-order, post-order, no. In order will sort the tree. Yeah, clear? Okay, now we go to the last one. So in the code, how to know whether the node is at the left or at the right? So later we will discuss the implementations. Okay, before we go to the code, we need to understand the concept first. Okay, later I will show you. Need to understand the concept first. Okay, back to the last one, post order. Okay. Last one. So post order is a bit different. We need to go to left first, go to the right, finally only the root. So the root will be the last element. So you can see post order, your root D. D will be your last element. So pre-orders, the root will be your first element. This is the difference. Post order, the root will be your last element. So what the post order do is, I need to go to the left first. After that, go to the left. A. So display A. So after finish display A, you go back to the root elements, but you can't display because according to post order, you need to visit the right. Okay, right. A C first. C first. So if no more elements, then only you display the root element. Okay. After display B, you cannot display D because D is the root element. So we need to go to the right. Right. This is F. Okay. So after you go to F, because you still have a right subtree, no left subtree, but there's a right subtree. So you must go to the right subtree first. Means you need to display G first, then only come back to display F, and finally come back to D. Okay. So post order is a bit different. You don't display the root elements if you consist of left child or right child. The root will be the last one to display. Okay, one more example so that you can understand. The last example, post order again. So P, they will go to left. Okay, no more B display. Okay, go back to the root. So root still got right subtree. So you go to right subtree. Right subtree still got left subtree. So I will display G first. After finish G, then I go back to H. No more. Okay, no more display. No more display. So B, G, H, F. B, G, H, F. Okay. Then I go back to the root, but this root still consists of right child. So I go to right child. This right child still consists of left child. So I need to display left child first. Okay, so after I display R, no more already. Go back to S, go to Y. So Y still consists of left child T. Okay, T, no more, left child. But there's a right child. So after R, I display W. Okay, W, then only T. Okay, T will go back to Y, but Y consists of a right subtree. So I need to display Z first, then only Y, then only S, and finally P. So this is the post order. Yeah, clear? So make sure you understand these three algo: pre-order, post orders, and in order. Okay, any questions before we proceed? This is a concept. So later we will implement in the code. Okay, next one is two type of binary tree. One is full and one is complete. Okay, different. Okay, what is a full binary tree? Okay, a full binary tree, this one is important. Okay, all of the leaf must be the same levels, and then each non-leaf node must have two children. Full and complete a bit confused, but the terms is for full, everything must be in the same level and all the non-leaf node must have two children. Yeah, this is the definition. Complete is different. Okay, complete is the leaf on the last level. Okay, the leaf on the last level must be as far to the left as possible. Means we need to fill up all the leaf in the left hand side before we fill up the right hand side. Means the left hand side one must be complete. The right hand side may be empty. Okay, so there's a formulas to calculate the height, okay, of a complete binary tree. Because this complete is not full, so the complete binary tree can have a 2 to the power of h minus 1 node till 2 to the power of h minus 1. So this is 2 to the power of h minus 1. This is 2 to the power of h minus 1. Yeah, so the node can be from here, the range, okay, because it's not full. Okay, let us look at the tree that is full and complete. These are the example. Okay, so this is only one root, so full and complete. Yeah, because this is actually the root and then the leaf also. Okay, this one, because the left hand side is missing, so it's not full and it's not complete. Yeah, this one is not full because the right is missing. Okay, but it's a complete binary tree. Why complete? Because the left one is already filled up. Okay, go back to the definition. With the leaf on the last level as far to the left as possible. So this one is complete, but it's not full. It's not full because this is missing. So complete, yes, is left subtree must be full. Okay, like this is full. Okay, you see, each non-leaf node, two children. This is full. So when the binary tree is full, basically is complete. But if the tree is complete, not necessarily is full. Okay, again, so I repeat, the condition is if the binary tree is full, definitely the tree is complete. But if the binary tree is complete, not necessarily the tree is full. This one you must understand. Okay, go to the E. Okay, E is not full and is not complete. Why? Because in the layer 2, the right tree is missing. But let's say if you have something like this, if you have a right tree here, this is complete, but it's not full. Okay? This is not full and not complete. Why? This thing missing. Missing the node here. Yeah, clear? Okay, D. Okay, what if the leaf on the D is not there? So if this thing missing, is not full, is not complete. One student asked, what if this node missing? Or these two node missing? If these two node missing, it's not complete, it's not full. Okay. If the last level consists of only one children, this one, this is the last level consists of only one children. This is complete, not full. C also don't have right node. C no right node, so complete, not full. Why E is not complete? Okay, E is not complete because this level, level 2, right node missing. This level. So if you want to fill out the left, make sure the top level must be full. Okay. Make sure that again go back to the definitions. Okay. The binary tree is either full or through to the next to last level, with the tree, with the leaf on the last level as far as to the left. Yeah, on the last level. So back to the E. E, the last level is correct, but the second last level is not complete. See? It's not full. No node here. So it's considered not complete. Yeah. So make sure this, if let's say this one left is full, make sure the previous level must be full. Okay. Otherwise, it's considered not complete. So if the thing not complete, so we can make a conclusion, the tree also not full. Okay. Any questions so far? Let give you a few seconds to digest. Yeah. Clear? So that's why this is the difference between E and F. E is complete, this level done. But this level, this one missing. Okay, what about E, the last right node disappear? The last right node. This one. Same thing. Same thing, also not complete. This thing missing. Just compare E and F. So if you have this, yes. Okay, so if F, this node missing. Complete or not complete? The cursor I point to here. If this thing missing, complete. Correct. Luckily got. Someone say no. Complete. Complete. Because this thing missing means your left actually fulfilled, but the right not necessarily. Then you just follow this. Follow this. This is complete. So if this thing missing, complete. Because the left is filled up the same level. Yeah, clear? Okay, can understand the concept? Okay, so after you done this, the next concept is usually when we implement binary tree, we create the abstract data type for binary search tree. Okay, binary search tree. Okay, wait, another question coming in. The last level go to the left node, while the others level having two children means complete. Means your previous level must have two children complete, then the last level must always go to the left. Yes, correct. Yeah? Okay, now we go to this one. Okay, so in binary tree, usually we implement the abstract data type for binary search tree. Okay, or sometimes we shortcut BST. Okay, BST, binary search tree. Okay, so what is binary search tree? So when you want to create a binary search tree, there are some rules we need to follow. Yeah, just like stack and queue. Okay, stack is last in, first out. Queue is first in, first out. So for binary search tree is when you want to insert a value, the values in the left subtree must be less than or equal. This condition importance. Whenever you want to insert a node, the node in the left subtree must be less than or equal to the values in the root nodes. Okay, later I will give you this example. And then if you want to insert to the right subtree, the value must be greater. Okay, the value must be greater. Okay, let us look at this tree. This tree. Okay, let me give you the example. Okay, basically, this tree is like this. Let me draw the diagram first. Anything. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So this is the numbers we want to insert to the binary tree. Yeah, a list of number. So randomly generate, and then we want to create the BST. Okay, BST. Okay, so according to the rules, BST is the left one must be less than or equal, and the right one must be greater. Okay, so we go to each node. So the first one is 9. Okay, so 9 will be your root element. So you insert 9 here. Correct. Okay, 17. Because 17 is greater than 9. So you put here. Yeah. Okay, next. 4. 4 is less than 9. So 4 you put here. Okay. Then 3. 3 is less than 9. 3 is less than 4. So 3 you put here. Okay, 6. 6 is less than 9, but greater than 4. So greater than 4, go to the right. Okay. Next, 22. 22 is greater than 9, greater than 17. Okay, put here. 5. 5 is less than 9, less than greater than 4, less than 6. So here. Okay. 7. Okay. 7 is less than 9, greater than this one, greater than this one. So put here. So 20, greater than this one, greater than this one, less than this one. So put here. Yeah. So one student asked, okay, let's say next one we have 10. Where is the element? So 10 means greater than this one, less than this one. Here. 10 will be here. Okay. The subtree, the left subtree of 17. Yeah. 10 is here. So imagine, how to draw 10 here. 10 here. Okay. Make sure now it's 10 here. Okay. Now, next, someone asked. So 9 again. Oh, 9 again. So 9 again. So 9 is what? Less than or equal? Equal. So 9 will go to here. Greater than. So 9 will be here. Okay. Let me print screen first. Okay. So just now the number is this one. Out here. One. Yeah. Okay. Wait. Come. Wow. A lot of questions coming in already. Wait. Okay, is it only possible to insert integer in the tree? No, you can insert string, you can insert characters, you can insert any variable type, or you can insert an object. So the object can compare some value. So it means we can compare. let's say anything you want to compare values or ranking, so we can use the binary search tree. Okay, means not necessarily numbers. Okay, can be a string, can be a characters. So the next question is, if have two equal value, okay, two equal value, nice. So always remember, less than or equal, less than or equal, go to left. Yeah, less than equal, go to left. Next. Okay, will the first number always be the root? Yes, the first number will always be your root. 9 will be always your root. Correct? Okay, 9 will be always your root elements. Okay, what if all number greater than 9? No more left subtree at 9. Yes, correct. If all greater than 9, nothing here. This left subtree is missing. Because according to the BST, you must insert the node greater than the root elements to the right. Okay. Why 9 become the root? 9 because it's first element. First element. Yeah, first element. Next one, how to compare string? Compare string. Not compare to use the compare to method. Okay, how to compare string using the compare to method. Compare to. That's why later in your generic type this generic type always in the tree must extend comparable. Later we will discuss the code. Okay, next questions. If want to compare, why use search tree instead of list directly? This is a good question. Let me copy. Yeah, the question is like this. Okay, if you want to compare, why we need to use binary search tree instead of list? Okay, if you use list, you need to compare one by one because list is a linear structures. By using tree, you can do half. Means you can search the left or you search the right. So the performance is better if you use BST compared to list. This question is very important. So that's why we need to learn when you do searching. Sometimes when you use tree is faster because you can go two-way, left, right, recursively. Later I will give you explain the code as well. Okay, so the orders of the input will affect the tree. Yes, definitely. This order. Okay. Means if you have another examples input, let's say the first input, if the first input is too big, all will go to the right. Okay, let's say your random number. Okay, example random number 0 to 100. Okay, so the computer generate, oh shit, the first number 100. No more left tree. Okay, no more left tree unless another 100 come out. But let's say the example like this, no no more left tree. This one will generate right. Everything go to right. No more left. Okay? The left subtree will be missing. So that's why the input of the numbers will affect the tree. Okay? Hey, sorry. No, correct. Confused. Means if your first number is 100, everything go to the left, no more right. Yeah? Okay? If let's say the first number is 100, everything will go to the left. Right? How to apply tree in COVID-19 assignment? Is there a title about COVID-19 in the assignment? Yes. Oh, okay. So for those doing the COVID-19 assignments, you try to email Dr. Liu. Try to email Dr. Liu because this one is his topic, I think. Try to email Dr. Liu because I haven't go through the assignment yet. Okay? So this is the example. Okay, let us continue the lecture. So it's a concept. Now we done the concept. That means go back to this one. So you must know two children. So all the nodes without children is the leaf, the height, then how to traverse to the tree, in and post, and then what is a full tree and what is a complete tree, and finally how to create a BST, okay, according to the rules. Clear? Okay, now we go to the code. So to create the binary search tree, again, first we need to come out the node, okay, the node. So according to the node, okay, from here you can see the BST node. This node will consist of left and right. Okay, another difference is here. This one. Okay, so before this, when we create the list node, you remember the list node, we use T only. Why? Because we seldom compare the values of the node. Okay, but for binary search tree, usually we want to compare the node, the value. Okay, so it's better to use T as 10 comparable T. Okay, why? You want to compare something later. Okay, this T value you want to compare, either a string, a numbers, and so on. Later I will show you in the implementations. So this node basically consists of two, left and right. Just like what we did in a circular linked list. Sorry, double linked list, not circular. Double linked list, we have previous link, we have next link. But for tree, we have left one, then we have right. Means the structures consist of three elements: the values, left link, and right link. So when we construct a new node, basically we have the value. So the second argument with the left link, the left hand side, and the third argument with your right hand side. Means your left child and your right child. Okay? Whenever you create a new node, you will create one link to the left tree and one link to the right tree. Yeah, clear? Okay, so this one is the same, set value, and then basically we can set the left, and then finally we can set the right. Yeah, clear? Okay, but another difference in between these BST nodes and list node is the toString. So the toString we don't display here. Okay? No toString in the BST node. Okay? Because the toString method we need to put in the BST implementations. Why? Because there are different way to display the tree. Like just now I mentioned, you have pre-orders, you have in orders, and then you have post orders. So that's why we don't put the toString method in the BST node. Yeah, clear? So this again, so three elements. When you create a node, so you have the values, point to the left, point to the right. Okay, and then the methods consist of set left and set right. So this is the basic. Okay, any questions before we proceed? Can a child has two root? Cannot. Yeah, the requirement already mentions. The tree only consists of one root. Hey, why got this question come up? Next Tuesday got class or not? Next Tuesday no class later I inform. Next Tuesday no class, definitely no class holiday. Can a tree contains more than one type of variables? The answer is yes. Okay, but this is another good question. Wait, let me copy. Yeah. Can a tree contains more than one type of variables? Yes. How to make a few variables? Okay, you must create a class. A class to include all the variables. Okay? Let's say you want to compare a ranking, okay? A ranking on let's say a car models. Okay? You want to compare the same CC, what is the horsepower and so on. So everything you create a car object. So the car object will be the values of your tree. So in the car object, basically you can compare the price, compare the CC, compare the engine, and a lot of things lah. Okay. So next one is what? Cannot understand. Without stating generic type, it's better to use generic type. The reason why is because we want to reuse. We want to reuse the node for many different types. I know what you mean. You don't want to specify this. Can, but it's very difficult later. If you want to insert integer, then you have to modify this. If you want the character, you want to modify. If you want the object, then you need to modify. So better use generic. Yeah? Yeah? Okay, now we go to the most important one. The implementation. Yeah, done. Note 3 elements only. Okay, next. Okay, next one is implementations. Okay, BST. BST. Okay, same thing. This is very important. Yeah, T extend comparability. Why? Because later we need to use the compare to method. Okay, we want to use the compare to method to compare the values of the generic type. Is it possible to compare non-numeric variable? Yes. String. We can compare string using the compare to method. Okay? Clear? Okay. This one later I'll inform this. This is the constant variable. This one, the reason why I put here is because later I want to display the tree in order, pre-order, and post-order. That's all. Okay? Nothing. Okay? But I want to make it meaningful. If the thing is post-order, so I display like this. Okay? So this is the constant variable. We don't care about this one first. Okay, now we look at this one. I think this one also. This is the important one. Okay. Okay, this one also for other purpose. Yeah, these three. Okay. The file, the queue, and the traverse is for some method. Later we'll go to it. The most important is this one, same thing. Yeah. But in BST implementations, we don't name it as header. We try to name it as root. Okay? So remember in the linked list stack and queue, we call it header. But in BST, we don't call header. Okay? We use another name. So we use root. Root. Because one root element. Okay? So after you declare the root, so again, constructor root equal to null is empty when root equal to null. Get size. Get size is a bit different. Get size. These two is the same. Just to check whether the binary search tree is empty. So we just compare root equal null. Okay, get size. So get size, we have two methods here. Okay. The first get size is basically I call from the tester class. So I want to know the size. So if you want to know the size, basically I will go to the root element, pass in the root element. So when you pass in the root element, basically they will call this recursive method. Okay. This one without arguments. This one is with arguments. Why is Qt? Later I will explain the Qt. Later. This one later. I will explain. Look at this one first. Get size. Okay, how to calculate the size? So to get the size, basically we send in the root value here. Yeah, you send the value. Because this get size is a recursive method. Okay, just to calculate how many elements in the tree. So if your root is null, return 0. Okay, otherwise, see, this is the recursive method. They will go to the left, go to the right. So each time you found a node, +1. Okay, so if the node is empty, no need to +1. To see how they calculate the size. Each time you go to the node, if the node is there, +1 means it's not equal to null lah. Then at the same time, they will go to the left and go to the right in parallel. In parallel. That's why tree, you need a lot of recursive method. Clear? Get size. Why need +1? Yeah, when you reach the node, if the node is consists of node means +1. You want to count, you want to count the numbers of elements in the tree. Yeah? If you don't +1, how you know how many is elements? Okay, wait. Let me go to here. Yeah, like this. I'll show you many like this. Okay. So get size. So I go to 9. Okay, 9 is not it's not now. 1. 1. Okay. So the recursive method will go to left. 4. 4 also no now. 1. Go to left. No more. Go to right. No more. Okay. Go back to just now the recursive method. The recursive method beside go to left, also go to right. 17, yes or? So 1. So total now is 3. Okay. Back to this. Means each time you visit a node, if the node is not now, +1. Okay. Hey, this one like linked list. Linked list is you go one by one. This one is you go left and right. Clear? Okay, next. Okay, next one. Okay, next one is contains. Okay, this contains method. Okay, what is this contains method? This contains method is to check whether the elements is in the tree. Okay? So the contains method basically will return a boolean, true or false. Okay, example. Let's say just now this one. Okay, I want to find 6. So the methods will give you true, 6, because you can find 6 here. I want to find 23. The method will give you false. Okay, so this is the contains method. Okay, so the contains method will give you true or false. Okay, so to implement these contain methods, I need to have another recursive method, find. Okay, so this recursive method will find the node and the value. Okay, example, you want to look for 6. So when you find the 6 will come here, then they send in the root element. So you see, when they compare, basically, they need to use this method. So if the value you want to find compared to the value of the tree is less than 0, means the value you want to find is smaller than the value in the tree elements. You go to the left subtree. Okay? Because the smaller number in the left. Later answer. Okay. So if the value you want to compare is greater than the value in the tree, so go to the right hand side. These two must make it clear. Okay, I repeat. So if you want to find a value, so if the value the one you want to find compared to the value in the tree is less than the value in the tree, so definitely you must go to left. Okay? If the value you compare is greater, then you must go to right. Yeah. The name no problem. You can use any name. Okay, how about the value is equal? See? True. Right? Return true. Means you find the value. Yeah. That's why binary search tree is very fast. You can go left and right at the same time. If not equal, also return 2. No. Not equal won't return 2. Okay? Not equal won't return 2. Not equal. This is not equal. Either greater or lesser. Okay? This one is already not equal. This 2 is not equal. They won't return 2 1. They'll go to 5, 5, 5, 5, 5. Until they find the node is null, then they return false. They cannot find anything. But if let's say they can find, means true. Yeah, this 2 is the not equal. Okay? You either go to left or you go to right. Yeah, clear? This one. So if T more than A dot getter will return positive. Yes, correct. Correct. Compare to. So if equal 0 means equal. Yeah. Is there any possible the question will give the BST not in order? Cannot. The BST must follow the rules. If give you not order, then we can't get the solution. Okay? When you create the BST, must follow the orders. Later only we insert. Not yet. Okay? Now it's just find method first. Okay, wait. Just now I think I missed one question. Wait. Let me go back to find. Okay, can we get the get size with arguments and find to private since they are not used in main class? Okay. This one, back to this one. It's better your get size no arguments when you call from tester class. Why? Because if you use this one, how you send in your node? So better, different. This one no argument. This is the one you call from tester class. This is the one you call inside your BST. Yeah. Otherwise, from tester class, you can't call this. Okay? If you only have this method. Okay. That's why usually for tree I have two methods. One is call from tester. One is run inside your BST. This is usually your recursive method. And then someone asks, okay, why this one need to find, this one need to contains? If one contains, you can put contains, no problem. Okay, just the name only. Okay, but always remember, one is to call from tester. Another one is to run recursively in your BST. Yeah. Okay. We proceed. Next. Okay. The next one is get elements. Okay. Get elements and contents and find is exactly the same. The only difference is get elements will return the value. Contents will return true or false. Okay. But usually we don't get elements. If you know the elements is there, means it's true. Okay, but just another extra methods. This one not important. This get element. Okay. because the value you want to find from the tree is actually the elements. But this one later we need to use for others purpose. Okay? So usually we use these two methods first. We want to find the value in the tree. Yeah? Okay, next. This one important. Okay, the next one is add node. Okay, so this add node again the same. This is calling from tester class. Okay, I want to add a node, or I want you if you don't want to use, you want to use add node also can, both. Yeah, no problem. The name nothing one. Okay, so the add node basically I call from the tester class. So by passing in the value let's say example just now I go to tester class dot add 9. Okay, add 9. So when you add to the BST, so this is the part we need to check. Okay, so if your root is null, okay, if your root is null, so you can straight away create. Okay, how to create? So A equal to new BST node, you pass in the value. So your left and right also null. Okay, your left and right also null. Okay, else if, so we need to compare. So if your value you want to insert is smaller or equal, see this one is a bit different compared to just now. Just now nothing, not smaller equal. This is we follow the rules. If you want to insert an element in the tree, if the value is less than or equal, you go to the left. Otherwise, you go to the right. Yeah, the insertion is different. Okay, someone asked, why there is no current node equal to current node dot next? Definitely not, because the one is linear structure. This is not linear. This is non-linear. What is non-linear? You can go to left or you can go to right. That's why you need a lot of recursive method. See? Okay? So you can see when I set left, here also I need to put add another recursive method. Add a dot get left bracket. Comma t. Call back the recursive method again. Go to the right, check again. Go to the left, check again. If not, go to the left, check again. If the value is more than the root, go to the right. So it's recursive. Okay, recursive. Okay. After you adding, return the value. Okay. Why we need to return the value? We want to check whether you can successfully insert the item or not. We want to check whether you manage to insert the node or not. Okay. So that's why we return the value. Yeah, clear? Okay, that's why I put a root here. We want to check whether you manage to insert or not. Okay, so means if this is the first element, so your root will be the root elements. Okay, that's why you need to return. Next, how you will be returned? Yeah? Return. Okay, every time we add a node, we are constructing a whole new tree from a root by setting root A by setting node. Yes, means because every time you see every time we go to the tree, we need to pass the root. Just like in linked list, your header is very important. In tree, your root is very important. Yeah, if your root is missing, the whole tree gone. So be careful. Okay. Okay. So wait. Now we continue. This one done. Okay. So add operation. So add operation, like just now I mentioned, we need to iterate the path from root to the insertion paste. So follow the rules. We need to follow the rules. Okay. The root will not be replaced by A. Yes, the root will not be replaced. Remember, the root will be always there. The root cannot be replaced. The root will be your first element, always your first element. Add node return type is void. So when returning A, we don't return the node to the tester class. Yeah. No. If this value is now, then you return something. But this value is not now. Okay, unless got errors. If errors, then return now. If no errors, they will return something. Okay. Clear? Add. This add is simple. We just follow the rules. If the value is less than or equal, we insert to the left. If the value is greater, we go to the right. Again, must use recursive method. See, recursive method. Clear? Okay, next. This is difficult. Root equal to A, yeah, at first. The first one. First one. Okay? First one, root equal to your A. Right? Okay? And then so on also the same because later you recursive. Yeah? When you recursive until the end also return the root. Okay, this is a difficult part. Okay, what I say difficult. Okay, let's go to remove. Okay, the move operation is the most difficult operations in tree. Okay. Before we go to remove operation, add first, this one simple. Okay, so add 5, so the root will become 5. Add 9, because 9 is greater, so go to the right. Add 7, so greater than 5, less than 9, go to the left, and so on. Yeah, clear? Okay, why do we need the root? Can we add node alone? Cannot. Okay, the reason why you need the root, then you look at this. If we look at this example, okay, each time you need to pass the root to the tree. Why? Because from the root, I have 2 paths to go, left or right. See, add 9, so I check the root first. Okay, the root is 5, so 9 is greater than 5, so go to right. Okay, the next thing, you must pass in the 5 to the recursive method. Then 7 will compare to 5. Okay, 7 is more than 5. Okay, go to 9. 7 is less than 9. Okay, go to left. That's why the root is very important. You must pass in the root. Okay, because they will traverse through the root, after that to the left child or right child, and so on. Okay, why root equal to root A, root equal to add root T? Okay, get back to this one. Okay, the add node and the add is 2 different methods. This add node is I call from the tester class. Yeah, when you call from the tester class, you don't send the root from your tester class. You send the value. This is the value. Okay, wait. I think you misunderstanding. Go to my tester class. Okay. So in the tester class, here, see. Whenever I call add node, I just pump in the value. I don't put the root here one. The root you cannot put here one. Okay. Here. The next question. The next question, okay, later I answer. Maybe can also. Wait. Later. Okay, wait. Come. Now we go to remove. The remove one is very important. Yeah. So the add operation is like this. So we just follow. Okay? Means every time you check the root and so on. Yeah? Clear? This add operation. Okay, next one important. Okay, the next one is complicated because when you remove a node from the tree, there are three conditions. Three conditions. Okay, let us look at the three conditions. The first condition is remove a leaf. This one is easy. So if the node is a leaf, you just set the node as null. Full stop. Done. Very simple. Okay. Next, remove a node with only one child. So the root, after you remove the root, your child will become the root. Yeah. Okay. How to know? Okay. The first condition. First condition. If I want to remove 5, so simple. Just delete 5. Okay, done. What's up? Okay, this is the first condition. When the node is the leaf. Yeah. Clear? Okay. The second one is you remove the node, but this node consists of one children. Example, this one. You want to remove 22, but this 22 consists of 20. So how to solve the problem? So after you remove this value is not remove, is to replace this value with 20. Then delete. This is the second condition. Yeah, because just now is 22, 20. So I want to remove 20, but you cannot remove 20 because your parents still there. So what you need to do is you replace your value, the 22 you remove, you replace your child as your root. Means your child now become the parents, become the root. Yeah, clear? This one also simple. How if when delete a node when with one child, the child have value less than the previous one? Same thing, no problem. Okay, like this. I think what you mean is like this, is it? So I want to remove 6. So 6 also consists of one child. So what to do? You take out 6, 7 you put on top. No problem. Yeah? This is the problem now. Okay, the next question is important. What if the root has a lot of children? Oh yeah, this is the most difficult one. Okay. This is the third condition. Okay, so the third condition is you want to remove a node, but this node consists of 2 children. Okay, how to do? Okay, so for this condition, what we need to do is we need to replace the value of the removed node from another node. This is the difficult part. It means let's say sorry again. Screen first. This is the difficult part. Okay, example 6. Okay, I want to remove 6, but 6 consists of 2 children, 5 and 7. Yeah, so what to do? So means we need to find a value to replace. Yeah, we need to find the value to replace. Okay, which value to replace? Is the next one. Which node to replace? This one, remember, the node you need to replace is the value, you see, the value closest to the one you want to remove. Closest, n less than or equal. Okay, look at this. Example, I want to remove Q. Yeah, but Q consists of two children. So I need to find a value close to Q. And this value must be less than or equal to Q. So in this example is before Q is P. So P will be replaced to here. Yeah. So if no P, we need to find O. And then if no O, we need to find before O is what? N, M and so on. So the value must be very close, the closest to the value you want to remove. This is the difficult part. Okay. Looking at the example is easy lah. Okay. So back to the questions. Okay. I want to remove 6. This one very simple. Okay. Remove 9. 9, 6 easy. Why? Because then the closer is here, just remove here. This is same thing like this. Okay. I change the questions. I want to remove 9. 9, So the closest to 9 is 7. So this 9 will take out. Okay. And then this 7. Oh, shit. Hey, why cannot move? Hey, it's a cursor for me to drag one. Never mind, 7 will come here. Okay, 7 will come to here. So this one take out, Okay, you see, now the root element becomes 7. After you replace, you see, the condition they still fulfill. All these 3, 4, 5, 6 also less than 7. Okay. So this is the 3 condition. Always remember these 3 conditions. Remove the leaf is simple. Remove a node with 1 child also simple. Remove a node with 2 children. That's the big problem. So you need to find the closest value to the one you want to remove. And then always remember, this value must be less than or equal. Clear? Okay. Now we look at the before we look at the code, concept first. Concept first. Concept first. Let's say this is the initial. Remove J. J is simple. See, J is the leaf. Pick up, no more. Easy, right? Okay. Then we continue. Continue from this diagram. Remove C. Okay, C is here because C consists of child A. So what to do is C will be removed and then replaced by A. So A will become the root element. Sorry, will become the elements here. Okay. C also easy. Okay, just replace C, become A. Clear? Okay, next. Remove L. L is difficult. Why? L consists of 2 children. So it's the third condition. So the one closest to L means before L is what? A, B, C, D, E, F, G, H, I, J, A. The nearest one is H. H. See? So when you replace H to L, because H also consists of F. This is the complex because H also consists of F. So thing is F must move on top, then H move on top. This is the difficult part. That's why some question ask, what if the node you want to replace has many children too? Then you need to recursive. This is another example, but this is only one child, easy. What if this also got two child? Well, then you have to do this another time recursively. Okay? Okay. After that, after I done L, the next one remove D. D is here. See, two children. Okay, this one simple because the one closest to the D is A only. So A. Okay, and finally remove A. A easy parents. So condition B. That's why the thing become complex is because the value you want to remove and the value you want to replace also consists of two children. Then you call again recursively. This is the difficult part. Yeah, understand? That's why 3 bit tough. And then 3 you must do it recursively. Okay? Just now got some question I haven't answered. Later I copy out first. Later if not too many also ask me about the return value one. Wait, copy first. Wait, later back. That one is small thing yeah. Okay, come back to the code. Now is the code. Code okay. So in this remove method, same thing. This one also call from the tester class. Okay, call from the tester class. Okay, look at this one. Why there's a file value here? This file value okay, wait. Let me go back to the instant variable. It's an instant variable. That's why I need a file here. Okay, why I need a file value here? Because I want to check whether you can remove a value. Yeah, so if the value is not in the tree, you cannot remove so they will return false. So if you can find the values in the tree, you manage to remove, then you return true. So this is I put in the instant variable here. Yeah, so it's not a local variable. So that's why I put here. So the remove method will return either true or false. Okay, yeah. Again, you see the remove method also return back a loop. Maybe not necessarily later. It depends because some student already suggest another solution. Later we'll talk about this at the end. Okay, come back to this one. Okay, same thing. So check value, same like add method. You need to check the value. Okay, so you compare to the left and then you compare to the right. So after you find the value you want to remove, see, I have another method. Yeah, because of the three condition. Not like just now insert. Add. So easy. After you find the place, you just add. Remove is different. After you find the elements, you need to check which condition this element. Is it a leaf? Whether they consist of children, one child or two children. So that's why another method. Okay, so when I call this remove node method, when I call this remove node method, so if a dot get left equal to now, means left no children, no children. So I go to the right, go to the right and check. Okay, then you recursively call the right one. If the right one is now, okay, if the right is now, means it's not no children. Okay, so if no children means you just return. This one same means if the left is now, you go to get the right. If the right is now, you go to get the left. This is the third condition. Okay. if the note consists of two children, big problem. Right? Okay. So what is the big problem means we need to replace the data. Okay. Which one to replace? So we need to get predecessor. How to get? This one. Okay. So the predecessor, because the value you want to find must be closest. The first step is you go to the left. Yeah, go to the left. How to know which value is the closest? Okay, you must go to the left. Why? Because the left one is the one less than or equal. This is the first one, first time only. Okay. Second time, you see, second time, I use a while loop, but this time I must go to the right. Confused already, right? Closest, okay. The first time you go to the left because less than equal. The second time you must always go to the right. Why? Because after you know the value closest and lesser or equal, you must go to the most the highest value because closest so you must go to the right. Go to the right. Yeah Hey, this one you understand or not? Okay any questions? Wait, come. Can you repeat? Okay, I repeat Okay. So the note you want to remove, you find you find. Oh, finally you managed to find the note. Okay, you managed to find the note. Okay. So if you manage to find the note, first step is we check. So if let's say this thing, the left hand side is now. Yeah, left hand side is now. So we return the right hand side. Yeah. But okay, then we check again. If let's say this one right hand side is now, so we return the left. This two code is to settle the first and second condition. Yeah. Yeah. Okay. Next, this is the one is tough. Okay, why is tough? Because this one I want to find the value to replace. So to find the value to replace, the value must be closest to the value you want to remove. And then this value must be less than or equal. So to know less than or equal, we must go to the left You cannot go to the right, right? The right is greater. So you go to the left. So when you go to the left, here, you must go to the right. Why? Because after you go to the left, these are all the value lesser or equal. But the most left-hand side one is the minimum number. The right-hand side one will be the numbers closest to the one you want to remove. That's why here must go to the right, go to the right. Okay? Finally, you managed to go get the data. Okay? So what you do, okay, you set the value and then you set left. You see? Set left. Set left is become the node you want to remove just now. Okay? Yeah, means you replace the value. This is the difficult part. Okay? For 3. Okay? Luckily, this semester is all online. Otherwise, want to write this code, must understand. Okay, the get line is because we want to find the closest value, the closest value. Okay. We use this one to yeah. This one. Like just now. This one too complicated because two value. Okay, this one. Let's use back this one. Back this one, Where's my here. Yeah. So we use back this value, okay, this one. Hey, so the question said I want to replace 9. 9, 9, okay. So 9 I is if A equal to now, okay, so it's not, so 9, this is 9, okay, the first one you find already 9, so A equal to remove node, root, this is root, okay, so come to here, root, so if A dot get left equal to now, no, this is not now. If A dot get right equal to now, no, this is also not now. So it will come to the third code, the third condition. Okay, third condition is I want to know which value I want to replace. So how? Go to the left. Go to the left, Go to the left. This won't make it minimize, like this. Okay. Yeah, go to the left. Yeah, means when I call the one value I want to replace, go to the left. 4, 4, 4. Okay, 4. 4, So 4, while A dot get right not equal to now. A dot get right not equal to now. 6, A dot get now not equal to now. 7, Okay, 7, A dot get right equal to now or equal to now already. Stop. So stop at 7 already. 7. So 7 is what? A dot get data 7. Return 7. Okay, so set data equal to 7. So where is the eraser? Okay. 1, 7, 7. 7, Yeah, clear? Next. Set data, set data 7. Okay, then A dot set left. A dot set left, A dot set left. This one, remove A dot get left T. Okay, so remove A dot get left T, this one, must repeat again, repeat again. Okay, this one, remove again. Okay, so this time remove what? Remove 7, because just now you replace already, so you remove 7, so you continue until the thing come to 7. 7 remove. Okay, job done. Wow, so many condition, wait, come one by one. Wait, I have only 20 minutes. I need to settle this one first. Okay, some of these questions, you ask me during your tutorial time, I finish first, later I answer if got time. If you have another 9 also the same thing one, the same algorithm you can use. Okay, if you have another 9 value, okay, but they will remove the first 9 first. So if let's say you want to remove 9, so if there are 2 9 in the tree, they remove the first one. After remove the first one, then you need to issue another command to remove the second one. They won't repeat. Okay, but you can use a while loop in your tester class if you want to remove all the 9. Okay, this one only remove 1. Yeah, clear? Okay, come next. Next. Wait. not in. Yeah, which slide any? Wait, this one important. Okay, the remove operation, you try to digest first. Okay, later I go back, come back again. Okay, maybe you can ask during your tutorial session. Okay, next one. Next one is the show operation. Okay, so like just now I mentioned, the show operations, there are a few methods to show the tree: in order, pre-order, and post-order. So here we need to use a queue to print the list. To print the tree. That's why in my code I have a queue here. Means we add the items to the queue, then from the queue we show the item. And then the type of travels, it depends on in order, pre-order, or post-order. Okay, in order, pre-order, or post-order. Yeah. Okay. So when we want to show tree, let's say I go to the method show tree. Again, same thing. The show tree, I will call a show queue method. Show queue method. So this show queue method, hey, where is the show queue method? Missing. Sorry. The show queue method is a queue. Before I show the tree, I need to set order first. Which order we want to display? You want to display in order, pre-order, or post-order. That's why I have three recursive method here: in order, pre-order, and post-order. So how to write this in order, pre-order, and post-order? Everything is simple. We just follow the algo. Okay. So we send in the root element. Send in the root elements. So if the root elements not equal to null, okay, we follow the algorithm. So the algorithm mentions pre-order is go to root, go to left, go to right. Go to left, queue the data, go to right. Yeah, easy. Left, go to root is actually this one. Left, print the data, right. So in order, root, left, right. Sorry, in order, left, root, right. So left, root, right. Okay, pre-order. Okay, pre-order is what? Pre-order is visit the root, left, and right. So root, left, right. Means root means you display the data. Before you display the data, I enqueue to a queue. And post order, same, left, right, root. This three method is easy. Because you just follow the algo. But they will call recursively. Call recursively until everything, then we can show the tree. So before I go to balance tree, let me show you the mean method. The mean, the example first. Show you example first. This is the example. So here I want to insert a random number to the node, to the tree. Okay. So you can see here. See, before I show tree, I need to set order first. Okay. Set order show tree. Set order show tree. Okay. So the set order method basically we'll call this method set. Okay. Set the tree, whether in order, pre-order, or post-order. Okay. After set already, I show the tree, show the elements. Okay, let us run the program. Okay, so insert 10 random numbers 0 to 20 into binary search tree. So the random number are these so 11 will be your root elements. Okay, so when you print in order, you can see the item is sorted. See, sort. It help you to sort already. 1, 1, 8, 9, 10, 11. So in order is sorted. Pre-order and post-order is different. So pre-order, you can see the root element always the first one. Post-order, the root element always your last one. This is how we arrange the tree. So when you draw this tree, let me see. Okay. When you draw this tree, something like this. 11 here, then 1, then 12, then 1, then 11, 1, 12, 1, 16, 16 here, and 10. 10 is less than this one, greater than this one, 10 is here. Then 15, 15 greater, greater, less. 9, 9 is lesser, greater, lesser. 8, lesser, greater, lesser, lesser. Not enough space. 8. Then, next one is what? 15, 15, 15, greater, greater, lesser, lesser, equal, 15. The 3 is something like this. Okay, so why you need to use a Q? Okay, because we need to put the item in the queue to print out. Or if you don't want case, queue easy lah, because you enqueue first in first out okay, and this is to show the items. Okay, next one is balance tree. Okay. I think I need 2 weeks for this. Yeah, maybe cannot finish. We will continue during the sorting chapter. Okay. I finish the balance tree first. The last one is the application. Application, we'll talk about it next time. Okay. Okay. To balance. Balance tree. Okay. Balance tree. What is balance tree? Balance tree is to ensure the numbers of descendants in each node left and right is even. So I try to even the tree. Not like this. This is not even. Means I want to make sure the left and right value almost the same to even out. But in order to even out, some of these elements you must remove or replace. Okay, you must replace. So how to replace? So in order to replace, we need to make sure that the middle elements become your root. So when the middle elements become the root, so your tree will be balanced compared to this one. You see, 11. 11 almost the middle one. You see, 1, 2, 3, 5. Almost the 12, 16, 15. 1, 2, 3, 4, 5. Almost the middle one. So by replace the middle elements as the root, so your tree will be more or less balanced. Okay, if your root elements is the rightmost, then your tree is not balanced. Okay, everything go to the left, subtree. So if your tree the value is too small, everything go to the right. So that's why in order to create a balanced tree, the middle elements must be the root. Yeah. So in the code, okay, so I did create how to create a balanced tree. Okay, you can have a look first. Okay, just to find the middle value. Okay, just like a binary search tree. Okay, how to find the binary key. Okay, and then there's a code also. Example code here. Wait, let me comment this out. Example 2. Okay, is to create the balance tree. Okay, example 2. Create balance tree. So in order to create balance tree, the tree must be balanced. So they will call this tree.balance method. This balance method is here. Okay, you can have a look. Okay, it's try to put the minimum as the middle elements as the root when I insert the tree. Okay, this is the part. And then You see, so when I insert the balance tree, 4, 7, 8, 9, 10, you see 10 is actually the middle element, the load. See, 10 become the load. This is the balance tree. Okay. So, okay, what type of application we can use for tree? Okay, so there are quite a numbers. The first one is actually we can use, we can represent the expressions. Okay, the expression using the tree. So when we represent the expressions, the operator, see, the operator will become your root. The operands will become your child. Okay, like this plus. Okay, example, you see, so R equal to 1 plus L minus 1 multiplied. See, L minus 1. L minus 1 is here. Okay, multiplied 2 plus 1. So the operator is your 3. Okay, can. Then another application, so BST can use to construct expert system. Okay, what is meant by expert system? Means this system will consist of a lot of questions. So if you manage to answer correctly, they will go to the left. That means I can create a system, expert system, means that to test whether you did the correct way or not, or correct survey, some survey. So if you answer the survey, let's say you follow this survey, this style, let's say there are different style, different human style. Sometimes they can make a guess. Okay, if your human style or if your human mind is like this, so the response is always go to the left, because you answer correctly. So if you answer wrongly, they will go to the right. Then if you answer correctly again, then they will try to go back to the left. So means we can use a BST to create an expert system. More to the AI things. Okay, very important this one. Okay, and then BST also allowed for fast searching, passing, binaries, search tree, very fast. Why? Because I can do recursive. I can recursively go to the left and right very fast. Okay. Uh, Expressions, like I say in the stack, when we use the stack to evaluate infix, postfix, so in BST also we can do the same thing. So, but in BST, what we can do is one stack you use to hold the arithmetic, another stack is you hold the binary search tree. Then you can use the pre-order, in-order, and post-order. Okay, this one we will do in the tutorial and lab questions later. Okay, show you more example. So this is one of the algorithm later you can implement in your lab. Okay, lab or tutorial, I forgot already. I put some of the algorithm. Okay, so as you can see, after you put okay, basically we can solve, okay, the or insert the expressions into the binary search tree. Okay, quite a lot of things to digest today. Okay, should put in 2 weeks later, maybe next year. Never mind. Okay. Okay. Now, still left 5 minutes only. So, is any questions? Yeah. Try to understand this part, especially the remove one. The remove. Okay. The remove part is the one is difficult. Okay. So, these two is to remove the one with one child or no child. This is the one to remove the one with two child. Okay. That's why in the remove method, there's a set left and set right. Wow. Any questions? Too many things to digest today. Okay, you try to do some revision first. If let's say you have any questions, you can ask during the tutorial section. We'll discuss more at that time. Yeah. Okay. So if no questions, we will stop here. So we will continue the tutorial and lab this week. Okay. Yeah. So we will stop the section here. Any questions? Okay. Thank you. Okay. See you this week lab. Okay.
For expert system. Okay. If the decision is yes, maybe go to left, otherwise go to the right. Okay. So um, this is what how you use a binary tree. Um, yes, lastly this one. Okay, please and actually the record the algorithm is here. You can read at your own. But basically the idea is you can use the expression tree that I mentioned just now. This one. Uh, sorry, this one. Okay. Uh, to form expression, and surprisingly, you may find out that okay, it's not written in the notes, but you can find out that if you write an expression, you write an expression in the expression tree, okay, and that expression actually is the infix expression. Infix expression, and you traverse it using the in order method. In order, okay, in order traversal method, you will have the infix. When the same thing, you traverse it using the pre-order method, you get the prefix. You traverse it using the post uh, order method, you get the postfix. Okay, so that's all. So I think I have to stop here. It's over time already. So thank you very much. And then remember next week. Okay, last two things I have to remind you. Next week no class. Okay, because it's a holiday, Hari Raya holiday. So we'll see on the 2nd of yes 2nd of June. Okay, and then lastly, remember to key in your yes like this. Okay, very good. So that I do not need to meet you every time. Okay, so anything else? So okay, if there's nothing, thank you. We stop here.